In this video, we'll go over the 4 common crystal structures that we see all around us: simple cubic, face-centered cubic, body-centered cubic, and hexagonal close-packed. In addition, we'll be going over their key material science properties that are important for understanding bulk material properties. But before I go into each of the crystal structures, I want to give an example of where we see them. Here is one of my favorite views of the Golden Gate Bridge. Here we can see not only the bridge itself, but also the bay and the steel structures that are holding up the bridge. If we zoom in to this part of the structure and zoom a little bit even more and go even more to the atomic level, we can find that the steel is mostly made of iron as well as carbon. And if we focus on the iron itself, we can find that at the atomic level, we start to see these blocks of crystal structures that are repeating within the steel structure, which is the iron crystal structures that are making the steel and is responsible for the steel's material properties and strength. For iron specifically, we have this type of crystal structure or cube where there are repeated units with the iron on each corner of this crystal structure cube, as well as an iron in the center. This is called the body-centered cubic, or BCC, and it is responsible for iron's crystal structure because this unit is repeated over and over again in order to make that bulk steel that we see on the left. And so this is an example of a common material that we use everywhere in our buildings, our homes, and it's important to understand how these crystal structures make up the bulk steel because they're responsible for key material properties such as the strength, how much stress can the steel take before it deforms, and properties like that. And so with that, we're going to go over how each crystal structure that we see, simple cubic, face-centered cubic, body-centered cubic, and hexagonal close-packed, make up the material properties that we see in our daily lives by looking at specific calculations that we start off with in order to understand these crystal structures. And so the first simple cubic is commonly seen in polonium. Face-centered cubic, or FCC, is what is responsible for making diamond and aluminum. Body-centered cubic, or BCC, for iron, like what we saw in the previous slide, tungsten and chromium, and then hexagonal close-packed HCP, zinc, and titanium. These are common materials that we see everywhere, and so let's first start off with understanding how each crystal structure is different and important calculations in order to lead into understanding how these crystal structures are responsible for material properties. And so with simple cubic, as the name says, it's quite simple, quote unquote, where we have atoms or an atom in each corner of the cube. Because it's a cube, each length of the cube sides are equivalent, and we call this A, or lattice constant. The first calculation that we're going to do for simple cubic is find the total number of atoms enclosed within the cube. So when we say enclosed within the cube, we want to find the total volume, what total fraction volume is enclosed within the cube in order to calculate the total number of atoms enclosed. And so to do that, we observe that each corner is intersecting 1/8 of the atom sphere, and we approximate the atom as a sphere. And so in order to calculate the total number of atoms enclosed within this cubical structure, we do 1/8 times 8, because we have 8 corner atoms. We multiply that and we find that there is a total of 1 atom, meaning 1 atom's volume, enclosed within this cubical structure. If we then move on using this 1 atom that we calculated and focus on the bottom face of our cube, we can find that this is what the bottom face of the cube looks like. And so on the left, this is what material science textbooks and curriculum usually show a small sphere on the corners of the cube in order to have a more clear picture. But in reality, the spheres are actually touching each other on the sides of the face. And you can see here that the spheres are touching here, where you can find that the radius of a sphere and the radius of another sphere approximately makes up the total lattice constant A, or the side of the cube. And so with that, we can find that 2r is equal to A. And so we can now calculate the atomic packing factor, or APF. This is an important calculation for crystal structures because it tells us how much of our cubical structure is consumed with the atoms itself. And so this will tell us how packed our simple cubic structure is with the atoms at the corners. And so to calculate this APF, we need to find the total atomic volume that's enclosed within the unit cell divided by the unit cell volume. And so we found in the previous slide the number of atoms enclosed within the cube, which will be useful for this calculation. So to find the total atomic volume, we find first the spherical volume times the number of atoms in the cube that we found in the previous slide. Divide that by the unit cell volume. To calculate this, we do 4/3 pi r cubed, which is the spherical volume, times the one atom we found in the previous slide, divided by A cubed, because this is a simple cubic structure that is a cube, and so the volume would be A to the third. And r is the radius of our spherical atom. We know that 2r is equal to A from the figure on the left, and so solving for r, we can find that r is equal to A over 2. And so our atomic packing factor, APF, of our simple cubic structure is 4/3 pi times A over 2 cubed times one atom over the total unit cell volume, or the simple cubic structure, A cubed. And so if we simplify this, it will be equal to pi over 6, or 0.52. We can multiply this by 100, and so this would mean that 52% of our simple cubic structure is consumed by the atoms itself. On the flip side, there's 48% that is not consumed by our atoms. And so 48% of the volume of the simple cubic structure is not where an atom is located or consuming that space. And so that is important for understanding, first of all, how much space is within this crystal structure, and how much can we put into the cube that is not already consumed by an atom. Moving on to face-centered cubic, we find that this is very similar to the simple cubic structure, except that each face of the cube has an atom placed at it. And so we have 6 extra atoms shown in this figure, with each atom at the face of the cube, therefore called face-centered cubic. To find the total number of atoms, we first find that the FCC structure has, similar to the simple cubic, 1/8 times 8, where each corner of the cube is intersecting 1/8 of the sphere. And then we add on 1/2 times 6, because each face of the cube, there's an atom, and it's sliced in half. So half of the atom is enclosed within this cubical structure. And so we do 1/2 times 6, because we have 6 atoms in total, each are at the face of the cube. We simplify this, and this is equal to 1 plus 3, which then is 4 atoms. So we have 4 total atoms enclosed within our FCC structure. If we do the same thing and we look at the bottom face, we find that there's a close-packed plane on the bottom of the FCC structure, where we can see that the atoms are touching each other. And so we need to find the relationship with r, the radius of the sphere, and A. And so what we can do is look at the diagonal line through the square. We find that this is the radius of the sphere, another radius of the sphere, another r, and finally another r. If we use Pythagorean theorem, we can find that because the lengths of the square are a and a, that means the hypotenuse is a times square root of 2. And so 4r is equal to a square root of 2. Going to the atomic packing factor calculation, we can find that from the equation, we know that the spherical volume 4/3 pi r cubed times 4 atoms, which we found in the previous slide, over A cubed, which is the unit cell volume. We know from the figure on the left that 4R is equal to A times square root of 2. And so solving for R, we find that R is equal to A times square root of 2 over 4, which then means our APF can be solved like this, where we put in R into our equation and simplify to pi times square root 2 over 6, which then means 0.74 or 74% of our FCC structure is consumed by the atoms themselves. And so therefore, about 26% is not consumed by our atoms, and so this is a more close-packed structure compared to simple cubic, especially because we have more atoms enclosed within our FCC structure. Going on to BCC, body-centered cubic, we find that this is also very similar to the simple cubic structure, but instead we have circle or sphere in the center of the cube. And therefore that's why it's called body-centered cubic, because we have an atom centered in the cube itself. Notice that we have here the A square root of 2, because this is still a cube structure with a lattice constant. There's a right angle, and so this length for the diagonal is A square root of 2. And we find the total number of atoms for body-centered cubic, BCC. We find that again, the corners of the cube, 1/8 times 8, because 1/8 of the volume of the corner sphere is enclosed within our cube structure. And because we have an atom already within the BCC cube, we do one whole sphere times one whole atom is in the BCC structure. And so therefore we have 1 plus 1, which then is equal to 2 atoms enclosed within our body-centered cubic BCC structure. With this, length is A on the side. We have a hypotenuse on the bottom, A square root of 2. And then to make the larger hypotenuse from one corner of the cube to another, we find that from the Pythagorean theorem, the hypotenuse length is A times square root of 3, and so we document that here. And so with this triangle that we drew, this right triangle, we can use this to find the atomic packing factor. Similar to the previous slides, we need to look at the relationship between R, the radius of the sphere, and A. We find that in reality, at this large hypotenuse, the close-packed direction is showing the spheres touching each other, where there is 4 R's, or radius, that are making up that hypotenuse. And so these 4R is equal to that A square root of 3. And so with this, we can calculate the APF and find that 4 over 3 pi r cubed times 2 atoms from the previous slide over A cubed. We then solve for R from the relationship shown on the left figure and find that R is equal to A square root of 3 over 4. We then put that into our equation and find that this is equal to pi square root of 3 over 8, or 0.68, 68% of our BCC structure is consumed by our atoms. And so moving on to HCP, hexagonal close-packed, we can see that this is quite different from the cubical structure, where instead we have an hexagonal prism, where you can see that the height of the prism is C, is length C, and this is an ABA stack structure, where the first layer, top layer, is a hexagon shape called A. We have a triangular second layer, B, and a hexagon layer again for the third, which is A. And so this is called an ABA stacked HCP structure. And so to calculate the total number of atoms for HCP, we first see that the hexagon length on the top layer is all equivalent. Because we know that this is 1/6 of the sphere, we do 1/6 times 6, which is the total number of atoms at each corner of the hexagon, plus 1/2 times 1, because the face of the hexagon is slicing the sphere in half. So you have 1/6 times 6 plus 1/2 times 1. For the triangle, because we have 60-degree angles due to the lengths of the triangle being equivalent, we then have 1/3 times 3, or 1/3 of the atom times 3 for each on the corner on the triangle. And then you repeat for A, which is the same as the first layer, 1 6 times 6 plus 1 half times 1. We then solve this and find that this is 2 plus 1 plus 3, which is then 6 atoms total enclosed within our hexagon structure. So now we can go to calculating the APF, or atomic packing factor of HCP. First, we need to calculate the ratio between C and A. So to do that, we need to understand the lengths within our HCP structure. We find that from the center of the HCP on the bottom to the side is A. Similarly, this length is B, and then the long axis height is C. We know that in HCP, A is equal to B but not equal to C, and so this is important as we go to calculate the APF. First, we need to understand the C over A ratio in order to calculate the APF, and so what we can do is draw a triangle pyramidal shape within our HCP structure. So we can do that by drawing lengths here, 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 and here. And we find that the length from this atom to the next atom in the triangle layer is A, and these are all equal to B, but not equal to C. So we extract that triangle pyramidal shape, and we know that the angle is 60 degrees, and because these lengths are equivalent, this is a triangle with all 60-degree angles. This shape is a triangle pyramidal shape, and so we have a pyramid kind of shape where the back line is kind of like a diagonal tilted. And so that's important to keep in mind as we go to the next geometry calculation to find the C over A ratio. And so what we can do is we can draw a line down from the top atom to the middle of the triangle. And this length is C over 2, or half of that C-axis line that we drew in the HCP structure. We know that if we go down, straight down, and we find this, draw this length from one atom to where it intersects with the C over 2 length, this is a right triangle, and this length is D. And so we need to find the relationship between C, D, and A in order to calculate our APF. And so if we look at that side triangle, we know that this is a triangle with all lengths A. If we draw that D, and so we're on the bottom face triangle, if we draw that D length and we cut in half the bottom length side, which is A over 2, we can find that because this total angle is 60 degrees, half of that angle is 30 degrees. And so using our cosine property, cosine 30 degrees is equal to adjacent, which is A over 2, over the hypotenuse, which is D. We can then solve for D, which is A over 2 times 1 over cosine 30 degrees. And so using this, we then move on to looking at another triangle relating C, D, and A, where we can see that this right triangle, C over 2, D, and A, using the Pythagorean theorem, we can find and put in what we know for D. Simplify that, and then we solve and look for the C over A ratio, which we find then to be square root 8 over 3. And so this is our ratio of C over A, which is about 1.63. And so we use this calculation to find our atomic packing factor of spherical volume times the number of atoms in the cube over the unit cell volume. We find that this is 4 over 3 pi over 2 times the 6 atoms that we found previously over the hexagonal prism volume that we need to find. We know C over A is equal to square root A over 3, which then can be solved as C is equal to square root A over 3 times A. And then we know the hexagonal prism volume equation is 3 square root 3 over 2 times A squared, which is the side length, times C, which is our height of the prism, where A is equal to 2r, because in reality the spheres are touching each other, and so there's two radiuses, radii, that are making up this A that is constant. We then put in all the information that we know into the equations of the APF and simplify this to then 2 pi over 3 square root of 8, which is equal to 0.74, or 74% of our HCP structure is consumed by the atoms themselves. And so with these calculations, we can summarize them with the close-packed crystal structure table shown here. Simple cubic showing 1 atom, 52% APF, FCC 4 atoms, 74%, BCC 2 atoms, 68% for APF, HCP 6 atoms, 74% for APF. And then we can also look at this thing called coordination number, or CN. What coordination number means is if we pick an atom within this crystal structure, what are the number of atoms that are closest neighbors to this atom? And so to calculate that for simple cubic, for example, which has a coordination number of 6, while FCC has 12, BCC 8, and HCP 12, what we can do is visualize it like this. So here I see a simple cubic structure. If I add more cubes, it'll look like this, and they're all simple cubes, and so this is all the simple cube stacked on top of each other. And so if I highlight and look at this center atom, what we need to do is find the coordination number of simple cubic. And so what I need to do is identify the closest neighbors and how many of those neighbors do I have, which in this case, the closest distance would be A. And so first I find that the closest number 1 is here. Another one is here, which is also length distance of A away. Third, fourth, fifth, and sixth. And so we can see here that all the orange atoms that are numbered are our closest neighboring atoms to this center atom. And so therefore from this we know that the coordination number for simple cubic is 6. We can do the same thing for other crystal structures like FCC, BCC, and HCP. It gets a little bit more complicated to visualize, so I can do that in another video if requested in the comments below. But this is what it would look like if you want to visualize a simple cubic coordination number is 6. And so coordination number is the number of closest neighbors that are near whatever atom that you choose within your simple cubic structure or crystal structure. So these are the basics of the 4 crystal structures that we see everywhere in our world. Simple cubic, FCC, face center cubic, BCC, body center cubic, and HCP, hexagonal close-packed. We went over the important calculations of finding the total number of atoms enclosed within each crystal structure, as well as the APF atomic packing factor that explained to us how packed or how much volume is consumed by the atoms of the crystal structure itself, as well as the coordination number CN, which is finding the total number of atoms that are the closest neighbors for an atom that you pick within the crystal structure. These are important calculations that we need to understand in order to better look at and understand how these crystal structures impact our bulk material properties, such as the steel that we saw in the beginning, as well as how these crystal structures are responsible for things like mechanical properties, stress, yield, how they impact how we can design materials in order to have certain goals such as strength or bendability, durability, and different properties like that. And so thank you for listening. Please let me know if you have any questions or requests for other videos in the comments down below. Thank you.